Okay. So, yeah.
Do you remember how you find the time shift by dividing by the time shift is?
Yeah, you divide the phase shift by the frequency.
And then when you draw the graph, you have one, so the time shift was 1.5 second, half a second.
Okay.
And you add it to the original.
Yeah.
Yeah. How do you solve that out? Because one term has pi in it, radians in it, one term don't. How do you solve it?
Like, give me an example of a cosine.
Okay, like, I think you had cosine 8 pi t minus 3 pi to the third.
Minus pi over 3?
Yeah.
Okay, so the frequency is 8 pi, which equals how many hertz? Right, I take this and divide it by 2 pi, so that gives me 4 hertz, which means my period is a quarter second. Right? Easy. The phase shift is minus pi over 3 radians. And how many seconds does that correspond to for this cosine? Right, I divide it by 8 pi. Right, I do. So my t shift is going to equal my phase shift divided by my frequency. So in this case, it's going to be minus pi over 3 divided by 8 pi. So the pi's cancel, and I'm left with minus 1 over 24 coulombs? Seconds. Okay, good. All right. I don't know. You got to ask. Okay, so if I go to draw it, where does my cosine start? Does my cosine start here? Like a regular cosine? No, only cosines with 0 phase shift start there. So where does my cosine start? At that time, 1 over 24 seconds. All right. So 1 over 20, so I'm just going to draw myself a line. 1 over 24. I'm going to draw myself a cosine, pretending that that all lines up and stuff. I'm not very good at drawing. Okay. And obviously the cosine keeps going. I'm just drawing one period for you. So, what's this time? Right, right. You know, this time has to be the period, which is 1/4. And therefore, by applying arithmetic, this number has to be 1 over 24 plus 1 over 1/4.
So you leave the
Yeah, I mean, what does it mean to have a period? A period means pick any point on your cosine, doesn't matter which point, and then until you get back to that point again, it'll be a quarter second. Right? So, you know, I could just as easily talk about this point. Right? From that point to, from that point to where the cosine starts repeating itself, 1 over 4 seconds. Right? It doesn't matter where you start from. So the period is a quarter. The time shift relative to 0 in this case is 1 over 24.
Yeah, in this particular example we did in class, it came as pi over 2 seconds as the frequency.
Pi over 2 seconds is the frequency?
Cosine 4t minus 2.
Cosine
4t minus 2.
Cosine 4t. Okay, so what's my frequency in radians per second? 4. What's my frequency in hertz? It's this number divided by 2 pi. So 4 divided by 2 pi is 2 over pi. Okay, whatever. It's ugly, but it's a number. Okay, and what's my period? Pi over 2. It's ugly, but it's a number. Okay, right?
Add them are like regular numbers?
Yeah, that's what they are. They're regular numbers, right? I mean, it's just you add them. And what's your phase? So your phase shift is -2 what? Radians. So therefore your t shift is going to be -2 over 4, which is a half a second. Okay, so you go, you draw it, right? You shift it by half a second, and then your period is pi over 2, which is about 1.5. So there you go. So there's a half. There's a half plus pi over 2. And that's it. Yes?
I got a question. On the previous example, where the period's a quarter, if we want to make that cosine function a sine, would we add a 16th to the phase?
Right. That's a cool question. Let's talk about that. Because sinusoids, sines are sort of a part of this story. We're just not telling that story.
Related to this question.
Yeah.
Do we really have to convert from sine to cosine or no? Like if this one was sine 4t minus 2, do we have to go to standard form cosine? Or
No, you could do, no, it works the same way with a sine. Like, yeah, if I, okay, let me answer your question, then I'll answer your question. Okay, just because I think it'll make it be a little easier. If I wrote sine here instead of cosine, the only thing that would be different, I mean, frequency, same. Same. The only thing that would be different is instead of drawing a cosine that's shifted by a half, I would draw a sine that's shifted by a half. Done. It's still 90 degrees out of phase with the cosine. Right. The 0 point is here. Right? Not here, because there's a phase shift. Okay, so that's that question. That's the sine question. So now your question was, if I go back to a cosine, what do you want me to do now? No, you want me to go back?
If we want to convert to sine.
Oh, if I wanted to convert that to a sine. Okay, so in other words, can I express this as a sine? Is that what you're saying?
How would you express it?
How would I express it as a sine?
Would you add the pi over 2?
Oh, or subtract it. Okay.
Figure with the new period.
Okay, so the period's going to stay the same. So let's start with something. Let's start with something easier, and then we'll talk about how to express that as a sine. Okay, so cosine theta equals sine of what? It's either theta minus or theta plus. Let's see if we can figure that out. So here's a cosine. Here's a awful at this. Here's a awful sinusoid. Okay. So if I take a sinusoid and I want to make it into a cosine, what do I have to do to it? Shift it left or right? If I want to take a sine, I want to shift it left. So it's going to be theta plus pi over 2. So what this says is, take a sine, shift it to the left, you get a cosine. Conversely, if you take a cosine and shift it to the right by pi over 2, you get a sine. That's how I read that. So, getting back to this expression, if I wanted to take this cosine and express it as a sine, I would say that is equal to, that is equal to sine of, so just now it's just plug and chug. It's whatever this stuff is plus pi over 2. So that's going to be equal to sine of 4t minus 2 plus pi over 2. Yes?
Doesn't that require the period to be pi?
Nope. Nope.
But then technically you're moving like a quarter, so can't you just move a quarter
Because a quarter what?
of the period?
It's radians. So that's what's cool about it is you're not applying a time shift, you're applying a radians shift. So a pi over 2 radians is always a quarter period. Right? If 2 pi is 1 period, then pi is a half period, and pi over 2 is a quarter period. So regardless of what the period is, right? Regardless if I give you a high frequency or a low frequency or whatever, I'm just saying bump it over by a quarter period. You're done. It's kind of cool. Like it's independent of the frequency. Yes?
Now my question, when we get into like the representing cosines as sums of complex exponentials,
Yes.
then do we have to be in cosine? So if we're given a sine and we want to express it in complex exponentials,
Yeah.
then we have to convert to cosine, correct?
Well, strictly speaking, you don't have to. You could.
It would be more mathematically difficult.
You could do it. You could do this all with sines. So like we could, if I gave you a sinusoid, you could express it as a complex exponential just by itself. However, by convention, we've all, like engineers, have all sat down and agreed that it's too much work to do it sometimes in cosines and sometimes with respect to sines. So we've all just agreed that it's just easier if we think of everything as a cosine. Like we've just picked that. So we're just, from now on, even if you have a sine, you are going to, even though you could go straight to complex form just from the sine, we've agreed that we're going to use the cosine as the standard base. So you're going to take your sine, convert it to a cosine, and then express it as a complex. And we'll do an example of that, yes?
So just randomly, so when you graph the phase shift of the sine, it's actually an odd function, so whatever is positive on the right will be negative.
How do you mean?
So since sine is odd, is an odd function,
Yeah.
so you have symmetry
Yeah.
about y is equal to x. So let's say you have, you graph the phase shift, and then you have at 2 hertz, you have something that's like 2.
Okay.
+2. On the left will be -2.
Yes, but not for the reasons that you're thinking. It doesn't have to do with the fact that sine is an odd function. Oh, it's true that sine is an odd function.
It's only an odd function without the shift, right? Once the shift takes place.
Right, once there's a shift, it's not odd anymore. Hold on to that thought. You're on to something, but I think it's going to make more sense in about like 10 minutes after I do a little bit more math. Can you hold off on that? Okay. These are great questions, actually. I'm happy to kind of keep working through this and building some fundamental understanding of how all this is put together. It's going to make everything that's coming a lot easier. All right. So let's kind of jump into, let's pick up with the complex business now. So here's what we were talking about on Friday. Basically what we said was, I'm essentially going to summarize the end of Friday's lecture. So essentially, because it happens to be true that that did I use e to the j theta or phi? Theta? All right. Because this is true, just write that down. I can't talk and think and write at the same time. Okay, so that's Euler's identity. So this is basically how to take so this is a complex number, right? It's got a real part and an imaginary part. Okay, and essentially all I'm doing is expressing it in polar notation. The only part that was new about that for you is that in a previous life, you may have seen this expressed as m angle theta. That's sort of like the old way of doing this. Instead of expressing our polar numbers in this form, we're going to express our polar numbers as a complex exponential. Okay, and believe it or not, this actually works, right? If you take the Taylor series expansion of e to the j, of like e to the t, and substitute in j theta and do all this math, this actually works. Like this isn't just some fantasy equation that some engineer put together. This actually adds up. Yes.
Isn't the top one in radians and the bottom one in degrees?
It does. I mean, it doesn't. Well, this is certainly in radians. This doesn't work on. Well, boy, you know, as long as you're consistent, I don't think it really matters. I mean, you could do this and just say, when I say theta, I'm referring to radians, and you know, I think it just matters as long as you're consistent. Okay, but we're always going to talk about radians. Okay, but in any event, because this is true, it turns out that this is true. Cosine of theta equaled, we said, a half e to the j theta plus a half e to the minus j theta. So because that, then this. And then we said, and remember, and we got this just by taking this and adding e to the minus j theta to it, and then the signs canceled out, and then we were left with this. And then we said, well, if this is true, then the more general cosine would be, let's see, we said k cosine omega t plus phi. That's our most generic cosine, right? Cosine has got three parameters. It's got frequency, phase shift, amplitude. Okay. Well, if this is true up here, then we said that this must equal k over 2 e to the j phi times e to the j omega t plus k over 2 e to the minus j phi e to the minus j omega t. We derived that in class at the end of class on Friday. Okay? And this is basically an extension of this, right? The only things that are different, I mean, if you can convince yourself that that equation is true, then the only jumps that you have to make to get to the next equation are, well, let's see. We put an amplitude out front, so your 1/2 became k over 2s. Okay, it just got scaled by a k. And then, if you remember, if we replaced our theta with omega t plus phi, so if I take my theta and replace it with omega phi plus t, I've got e to the j, look at this, I've got e to the j omega t. That's what I get by sticking a, remember, replacing this theta with a omega t plus phi. So there's your e to the j omega t is right here. And your e to the j phi is right there. Okay, so it's all accounted for. It's just a substitution. All right, and the last thing I did in class on Friday is I said, ooh, look at this. All right, I noted that if you compare this number and this number, they have an important relationship. They're complex conjugates. Okay, they have the same magnitude but opposite phases. So just to remind you, complex conjugate if you've got x equals a plus jb, its complex conjugate x star, this is in rectangular form, it's going to have the same real part but opposite imaginary part. That's in rectangular form. Alternately, in polar form, if you've got x equals m angle theta, its complex conjugate is m angle minus theta, right? That's just standard definition of complex conjugates from, I don't know what math they teach that in, but, that should be old hat for you. So we finally said, okay, this is actually pretty slick.
So you can rewrite that as me j omega, and the complex would be me minus j omega?
Yeah. So putting it all together, I'm going to say that k cosine omega t plus phi equals a e to the j omega t plus a conjugate e to the minus j omega t, where a is defined as, what's my definition for a? Right, I mean, this is it. I got tired of writing that, so that's a. Right? So where a equals k over 2 e to the j phi. You with me? Man, that seems like a lot of work, right? I mean, what? I had a nice cosine. Why'd I have to go make it complicated? All right, I'll show you. So, let's do an example, and then hopefully this will make a little bit more sense. So that was basically Friday's lecture. So let's start with a cosine. Actually, let's use one of the examples that we were just talking about. What was it? Cosine of What was the other one? 8 pi t minus pi over 3. I don't know. Let's stick a number out front. How about 5? That's a nice ugly number for you. So let's express that in its complex conjugate form. So let's just go plug and chug. What's A? Well, actually, let's start with this. Let me do the first example like in totally in pieces. So we really can't make it plug and chug. What's K? And omega? And phi? Minus pi over 3, right? We got to make sure to pick up the minus sign. Don't lose the minus sign. Minus sign's our friend. Okay, so according to that, what is A? Right, exactly. It's k over 2. So in this case, it's 5 halves e to the j minus pi over 3. Yeah, we don't even need to write the conjugate, right? Because we know what a conjugate is. Okay, so x of t, we're going to be able to rewrite that as a e to the j 8 pi t plus a conjugate e to the minus j 8 pi t. And we're done. Now, here's why we wrote it like this. Here's why I went to all that trouble for you. You remember how I said that those plots that you've been looking at in the book and everybody's been harassing me like, what goes on those y-axes, right? Where'd you get that number from? Well, let's find out. So let's go ahead and examine this cosine from the frequency in the frequency domain. Let's make a frequency plot of this cosine. So remember, we always have to make 2 plots, right? You can't beat the fact that you have to make 2 plots. A plot that tells you about the magnitude and a plot that tells you about the phase, right? Because 2 cosines can have the same amplitude at the same frequency, but they can have different phases. We did an example of that, I think last Wednesday maybe. So unless you actually draw the phase as well as the amplitude, you don't really know what's going on. So here's my frequency axis. So let's start with the magnitude plot. Okay, so let's just focus on this equation. So where is the first frequency where I have stuff? Absolutely. So look at this carefully. See my expression? So it's always e to the j omega t. So the first omega where I've got some action is 8 pi. So I guess we'll make this in radians per second. I could do this versus hertz if I wanted as well. I would just convert that 8 pi into 4 hertz, but it doesn't matter. Okay, so I'm going to come over here to a frequency of 8 pi. And what's my magnitude of A? What is the magnitude of A? So here's 8 pi. So here's a question I'm essentially asking you. At a frequency of 8 pi, A tells me how much of it I have. Right? If A is a small number, then I don't have a whole lot of 8 pi. If A is a big number, I do have a lot of 8 pi. So how much 8 pi do I have? I have that much. How much 8 pi do I have? Well, I look at the coefficient of the 8 pi term, and I see that the coefficient is A. And how much of it do I have? 5 halves. So I come over here, and I draw myself a little stick, and I say 5 halves.
So we're not just taking that whole constant number, because that's a number that's just a complex number.
Right. Well, we're going to deal with a phase in a minute. But right now, I'm just looking at the magnitude. And the magnitude is the stuff that's out front of the e to the j pi. All right. We'll deal with the phase momentarily. Okay, now, There's another frequency here. Is this the only term? We dealt with this term. Am I done? Yes, I have another frequency. Look, I have another frequency. What's my other frequency? Negative 8 pi. This is where it starts to get weird. Okay? I got a positive frequency. I got a negative frequency. Right. So how much negative 8 pi, how much cosine or how much signal do I have at negative 8 pi? Well, look at the coefficient. The coefficient tells you how much you have. Okay? I've got A conjugate. Okay? Well, A conjugate is 5/2 e to the positive j pi over 3, right? Same magnitude, opposite phase. So, the magnitude that corresponds, so how much negative 8 pi do I have? I've got A conjugate, and the magnitude of that is also 5/2. This will become a little less weird as we move forward. Okay, so let me just summarize. We're not done, but let me just summarize where I am so far. Yes?
So if you have another signal, let's say 6 cosine A pi t in the same phase, you draw another magnitude plot for that one too?
Yeah, we'll do that example in a second. Yeah, hold that thought. Okay, so here's what I've done. I started with a cosine, and I said that's fine and everything, but let's express it as a complex exponential. Expressing it as a complex exponential revealed that although I started with a pure tone cosine, essentially what I'm writing it is a sum of two different frequencies. E to the positive, I'm writing it as complex frequencies now, of which I have two. I've got 8 pi and minus 8 pi are my two frequencies. And the coefficient tells you how much you have. It's like a multiplier that tells you how much you have of that frequency. Okay? Well, in this case, so then you just look at the coefficient, and that tells you how much you have of it. Okay, in this case, it was 5/2 and 5/2. Okay, now we need another plot, because it's not enough just to look at the magnitude, right? You've also got to look at the phase. Oh, gee, oops. Because I know how much 8 pi I have, but I got to know if there's a shift associated with that 8 pi. So once again, right? I don't have to guess. I just have to read right off my diagram. How much 8 pi do I have? I look at the coefficient, A. So here's A. Well, I'm done looking at the magnitude. I already did my magnitude plot. Now I'm doing a phase plot. So all I'm going to do is I'm going to say, how much phase is included in A? Right, forget the J. Oh, how am I going to do that? Right, how much phase do I have at 8 pi? Minus pi over 3 radians. So I come over here to my diagram, and I say, okay, at 8 pi, I have minus pi over 3 radians of phase shift. What about at negative 8 pi? How much phase shift do I have at negative 8 pi? Positive pi over 3. Right? Once again, I come over here. I've got negative 8 pi. That tells me the frequency that I'm dealing with right now. How much negative 8 pi do I have? A conjugate. The phase of A conjugate is positive pi over 3. Come over here. And we're done. Crazy.
So which plot is that as the...
This is the phase plot. We have a magnitude plot. We have a phase plot. Now, some thoughts. If you know A conjugate, right? So if I'm trying to communicate to you, like think about communication, right? This is all about trying to send information from one person or one party to another party. If I'm trying to communicate to you that I've got some stuff going on at 8 pi, I need to tell you how much of it I have. So I need to communicate to you A. Do I also need to communicate A conjugate? No, because if you know A, you know A conjugate, right? So really, when I'm describing, just conceptually, when I'm describing x of t to you, it's enough to tell you that I've got A e to the j omega t, or in this case, omega is 8 pi, right? The other half of the equation is, like if I tell you this, you know, right? You know that by definition, I've also got a conjugate of e to the negative j omega t as well. So there's a compactness to this, right? I really only have to tell you this much, and then you can just figure out for yourself that I had to have the other half as well, because you can't have one without the other. Right? That's how cosines are built. You can't have one without the other. So if I tell you this, this is assumed. And we'll see what the implications of that are in a minute. All right, questions? Yes?
So the A conjugate over there, you take it with the minus sign?
You take
In front of J?
this minus sign?
Yeah. So then you wrote it down.
That tells you the negative. That tells, well, there's two minus signs going on, so I don't want to mix them up. Okay, so this minus sign refers to the frequency, right? I mean, look at the equation. It's A e to the j omega t plus A conjugate e to the minus j omega t. So look at the t here, okay? You look for the t, and then whatever's dangling next to the t, that's the frequency. Okay, so right now, this negative 8 pi is telling me the frequency of interest. Negative 8 pi. So there's that negative 8. This negative 8 pi came from that negative 8 pi. Okay. Then you have to answer the question, how much negative 8 pi do you have? Well, this answers that question. How much negative 8 pi do you have? Well, you've got that magnitude, 5 halves, and this phase, pi over 3.
My question was the plus. That's all. Is over there that you replace the minus with the plus.
I'm sorry.
Here,
Here,
like you wrote the equation A equals to the plus sign that was is replacing the minus sign.
this plus sign?
It's replacing the minus sign of there.
That's replacing this minus sign?
The minus sign followed the J.
This minus sign.
Yeah.
Okay. This minus sign is here to modify this 8 pi. Okay. That has nothing to do with any pluses or minuses in the A. Okay, actually, let me do this. How about we extend the example, and maybe it'll make a little bit more sense. So hold the thought for a second, and let's see if this helps a little bit. So what's the easiest way to do this? Okay, I'm going to do a little bit of erasing, not much. So let's keep our cosine, but let's add another term to it. So instead of x just equaling this cosine, let's add to that 3 cosine 10 pi t plus pi over 4. So now I've got x of t is a sum of two cosines. Right? If I wanted to, I go to MATLAB and plot it, right? Just type in 2 lines of code and it'll give me a plotter. You can plot it on your calculator, right? It's got some squiggles in it, for sure. In fact, maybe we'll plot that if we have a little time. Okay? Now what I want to do, my goal is to make a magnitude and phase plot that correctly indicate to me the frequency content of this signal. You with me? So, the good news is we've already done the first term, right? That's already plotted. I already know how much 8 pi I have and how much minus 8 pi I have. Okay, yes?
Would the 10 pi change the position of 8 pi now?
Nope, they don't affect each other. The 8 pi and the 10 pi are independent.
They're independent.
Yeah.
You're adding them up.
Yeah, absolutely. Right? I mean, this is essentially, I'm asking two questions. How much 8 pi do I have? I've got this much 8 pi. If I then go and add on top of that some 10 pi, I've still got the same amount of 8 pi. Right? It's like if you're making a soup and you've got, you put 3, or a stew or whatever, you put 3 potatoes in there and then 4 carrots. Adding 4 carrots doesn't change the fact you have 3 potatoes. Right? It's the same thing, right? I mean, I've got this. It doesn't matter what else I throw on top of there. I've still got that. That doesn't change. Okay? They just add. Okay. So let's figure out how much of this other cosine I have. So let's go ahead and write that as a complex exponential. This will be my scratch paper over here. So I've got 3 cosine 10 pi t plus pi over 4. So what's my k? And my omega? 10 pi. And my phi? Positive pi over 4. Therefore, my a is equal to 3 over 2. And my, this is awful at this, aren't I? E to the j phi. Okay, so it's 3 halves e to the j pi over 4. Okay. Now watch. Here comes the magic. When I write this in a complex form, this is going to have a e to the j 10 pi t plus a conjugate e to the minus j 10 pi t. So, where's the first frequency where I have stuff? Let's start with the 10 pi. Clearly, I've now added some stuff at 10 pi. So I'm going to come over here to my picture, and I'm going to find, let's see if I can do this precisely. See, that's 4, 2, 4, 6, 8. Okay, so this will be 10 pi. How much stuff do I have at 10 pi? That's how much stuff I have at 10 pi. Okay, so let's see, if that's 5 over 2, 1, 2, ugh. How do you divide things into 5s evenly? Let's see, that's halfway, so I need 1, 2, 3, 4. All right, I can live with that. Good enough. Okay, so 1, 2, 3. I'm just trying to make my graph roughly to scale. Okay. That looks like a bus ran over it, but whatever. Okay. You with me? That make sense? Good. Let's do the phase while we're at it. So I'm still dealing with my 10 pi. I've just described to you how much magnitude I have of it. What's the phase of it? Positive pi over 4. So I'm going to come over here to my diagram. I'm not going to try to make this to scale. So here's 10 pi. How much 10 pi do I have? From a phase perspective, we said pi over 4. So let's see. Is pi over 4 more or less than pi over 3? A little less. All right. Pi over 4. You with me? Okay. Now, am I done? No. I've described how much 10 pi I have. Now I got to describe how much minus 10 pi I have. Okay. Well, how much minus 10 pi do I have? What's the magnitude that corresponds to my minus 10 pi? Right? Because if this is A conjugate is going to have the same magnitude and the opposite phase. So the magnitude that goes to negative 10 pi is still, where am I? Negative 3 over 2, oh sorry, it's still 3 over 2. And my phase? What's the phase that corresponds to negative 10 pi? Minus pi over 4. And we're done. So does that kind of help clear up the minus signs a little bit? So now what's cool about this is you've got a plot, right? And you can look at this plot and be like, it is very quickly apparent what's going on in this cosine, right? If I look at, forget the phase for a second. If you look at that magnitude plot, it's easy. You look at it and you say, oh, well, there are two frequencies, 8 pi and 10 pi, and there's a little bit more of the 8 pi than there is of the 10 pi. Okay, done. And if I wanted to make some inferences about the phase plot, it's the same thing. I've got two frequencies, and one's got a positive phase, and the other's got a negative phase, and you're good to go. Yes?
Pretty much. So you mean when you check a graph, you never care about anything but the frequencies of a full cycle.
Right. Right. So basically,
technically we don't when we check a graph. We do care about like other other frequencies than
right.
like 8 pi and 10 pi. Like sometimes you might care about it.
Right. No, that's exactly right. So let me kind of tell you where we're going with this, because I think a little context will help. Actually, let me see if I have this example on my laptop, because if I do, I can show it to you, and hopefully maybe that will give you the perspective of where we're...
Like halfway to the 8 pi, like 4 pi.
Right, there might be some stuff at 4 pi, right? But is there any 4 pi in this signal? No. In this signal, it just turns, I mean, I've picked it, like this is a silly case, right? It's only got 2 pieces to it. But we're going to start looking at progressively more sophisticated signals. And as we start looking at more sophisticated signals, they're going to have more and more frequencies in them, right? And then that's, you know, then this stuff will be a little bit more meaningful. Let me just check to see if I have this here, because if I have this, I think this will make a lot of sense. Really? I would have thought I would have had this on this computer. I bet I could pull it off a blackboard. Hold on a second. All right. Okay, I'm not going to waste time searching for this. We'll run the demo on Friday when I get here. I'll have it, make sure it's loaded on this machine. But yeah, basically, let me give you a better example. Right now, I'm giving you signals that are, I mean, they're Mickey Mouse in the sense that I've constructed them just to kind of make a point. Okay, but where we're going with this is, and we'll get there pretty soon actually, is what if I were to give you this signal? See any cosines in it? It's periodic.
You can add up a whole bunch of cosines to approximate it.
Right. So there's this cool theorem that we're gonna deal with that says, look, here's a signal. It's periodic. It turns out that I can recreate this exact signal with a sum of cosines. Right? And I swear you would not believe that you can get a sharp edge here by adding a bunch of cosines. But I promise you it's true. Okay? You'll see. All right? So take this signal. You can express this as sum of cosines. All right? So essentially what the analysis that we're going to get at is that you're going to look at this, and instead of seeing this plotted versus time, you're going to make your eyes swim a little bit, and you're going to see it in terms of frequency. So instead of having 2 sticks here, you're going to have a whole bunch of sticks. Okay? And some will be big and some will be small. and they'll be at all sorts of different locations. But this essentially gives you a graphical representation of what's going on inside this signal from a frequency perspective. It gets nuttier. You want to hear how it gets nuttier? This signal is periodic. Okay? So, I mean, I can do a little hand waving and convince you that you can express this as the sum of cosines, because at least it's periodic and a cosine is periodic. But it's also true that I could give you this signal as a function of time. Is it periodic? You can still express it as a sum of cosines. I promise you, you can make this by adding together regular old Mickey Mouse sine waves, cosines. As long as you know which frequencies to use, right? Because you may not want some frequencies, right? It may only be some, may only be others. But as long as you know which frequencies to use and how much of each frequency. Right? Some frequencies you might want a lot of. Some frequencies you may only need just a teeny weeny bit of. Right? You got to tweak it just right. So when I say which frequencies, that's essentially saying omega. And when I say how much of each frequency, that's basically A. Okay, so we're making a recipe. Okay? In this case, I only needed 2 ingredients in my recipe. All right? But if I'm making a more sophisticated dish, I might need more. I might need some of this cosine and some of that cosine. None of that one over there. Okay? I might need this cosine in this amount and that cosine in that amount. Okay? You add it together, you tweak it, you get a signal. So the whole point of this analysis is using tools that can say this signal can be expressed in the frequency domain, and then this gives you a graphical representation of what's inside of it. This is the recipe book. Okay? So, a parting thought. Bless you. Let's look at this for a minute and tell me if you notice a pattern. What's the... So I'm just going to tease this. We'll talk about this more on Friday. What do you notice about the magnitude plot?
Symmetrical.
Symmetric. Does everybody notice that? It's symmetric. We might even say that it's an even function. That's the fancy pants way of saying it. But symmetric is just as good in my book. Symmetric. Okay, it's symmetric. Why is it symmetric, do you think? Mm-hmm. Yeah?
Because the way we added the cosines, we had a plus. Over there we have a plus, and then when you get the complex conjugate, it doesn't change the magnitude of A.
There you go. Right. So you've always got omega and negative omega, and if you look at their magnitudes, they're the same. They always have the same magnitude. So of course, if you've got 5/2 worth of 8 pi, you've also got 5/2 worth of negative 8 pi. They're symmetric. So you're always going to get that symmetry.
You say because cosine's an even function and not the only
Yes. Exactly. Well, actually, no. That's not the reason. Cosine's evenness doesn't affect the magnitude, because you would get the same thing if you did this with sines. Okay. However, look at the so the magnitude plot is always even. What about the phase plot? What do we notice about that? Does it have symmetry? Yeah, it's a mirror image. It's symmetric. There's a lot of ways of thinking about it. It's basically symmetric across this line. So it's like over here, if you take the right-hand side and you flip it over, you get the left-hand side. Over here, you take the right-hand side, flip it once this way, and then flip it down, you get the left-hand side. That's also a kind of symmetry. It's called odd. Right? That's odd symmetry. Is that an accident? No, for the same reasons, right? If you've got the only difference between omega and negative omega from the phase perspective, because you know A and A conjugate are conjugates, the phases are going to be opposite by definition, because they're complex conjugates. So if I know that my phase corresponding to 10 pi is pi over 4, then by definition, at negative 10 pi, I have to have minus pi over 4. It has to be that way. Okay, so there's your parting thought. The magnitude plot always shows even symmetry. The phase plot always shows odd symmetry. And there you go. See you on Friday.
So, did you say that this is only one phase?